Hello everyone. Earlier we have discussed about optical instruments of microscopes, in which we have discussed about simple microscope and compound microscope. Simple microscope uses one convex lens of short focal length, whereas compound microscopes make use of two lenses, right? One is called as the object lens, other one is called as the eye lens. Object lens is of short aperture and short focal length, whereas eye lens is of uh, short focal length and large aperture. There we have discussed the magnifying power of that compound or simple microscope for two situations: when final image is formed at the least distance of distinct vision, or the final image is formed at the infinity. The state of image formed at infinity, it is called as the normal adjustment of the microscope. Now we will discuss about telescopes, which are of two kinds, the astronomical telescopes and terrestrial telescopes. Here we will talk about astronomical telescopes. Terrestrial telescopes are the one which are used to see the objects on the surface of the earth, distant object on the surface of the earth. The purpose of telescope is to make the image of a distant or very far off object at a near point, or to see the image of a very faint object which otherwise is not visible clearly. So telescopes make clear and bright images of all those faint objects and make these objects visible clearly. So here we will talk about the astronomical telescopes. So here it is the ray diagram for the image formation in case of astronomical telescope. However, there are again two cases of the image formation. First one is when the image is formed at the infinity, which is called as the normal adjustment, and other one is the image formation at the least distance of distinct vision. In both cases, we will find the magnifying power, or we can say angular magnification of the telescope produced by the telescope in the object. So in case of telescopes, again there are two lenses. One is called as the object lens, which faces the object, or we can say which collects the light rays coming from the distant faint object, and other lens is called as eyepiece, through which the final image is seen. Object lens, it is of large aperture and large focal length, whereas eyepiece is of short aperture and short focal length. The aperture of objective or object lens in case of telescopes is kept or used of large aperture because a large aperture lens can collect a more amount of light coming from that faint object, so that even the faint object is clearly visible, just like a faint distant star. Now we proceed to define and find the formula for the angular magnification or magnifying power of the telescope in the two different situations. The very first situation we will take, it is the normal adjustment. So normal adjustment of the telescope is the one in which final image is formed at the infinity, right? So how do we define the angular magnification in that case? It is defined as the ratio of the angle made by the image at the eye as seen through the telescope, right, to the angle made by the object as seen directly, when both object and image they lie at the infinity. Object it already lies at the infinity, and here in case of this telescope, when the image is also lying at the infinity, in that case the ratio of the angle subtended by the image to the angle subtended by the object, it is called as the angular magnification of the telescope in normal adjustment. Once again, angular magnification in case of telescope when the final image is formed at infinity, or we can say telescope is in normal adjustment. The angular magnification, it is the ratio of the angle subtended by the image at the eye or the eye lens as seen through the telescope, because we can look at the image only through the telescope, to the angle subtended by the object which can be seen directly when both the object and image are at infinity. So this is the this is nothing but the condition in which we are defining the angular magnification or magnifying power. In the last of this statement, this line, it is nothing but the condition under which we are defining the angular magnification of that particular optical instrument, whether it is a telescope or it was a microscope. So by definition, angular magnification M, capital M, it is given by beta angle made by the image divided by alpha angle made by the object. And because these angles again remain quite small, so they can be replaced by their tangents. So alpha can be written as tan alpha and beta can be written as tangent beta. Now this is the ray diagram for the normal adjustment of the telescope in order to form or make the final image at the infinity. So the light rays are collected by the object lens in case of telescopes, which are coming from a faint distant object. So when an object lies at very far off point called as at infinity, all the light rays coming from the object are parallel to each other, right? So all the light rays are collected by this object lens, which because of for an object which is lying at infinity, the convex lens, object lens, it is a convex lens. It makes the final image, or we can say it makes the image of that object at its focus. So for this object lens, the focus is f0. It is here, right? So here is the image formed of that distant object at this point f0 at the focus of this object lens. Now because final image is formed at infinity, that means for the eye lens, this object will be lying at its focus, because when object lies at focus, only in that case the image is formed at the infinity, right? So this image by this object lens is so formed, or the distance between this eye lens and the object lens is adjusted so that the final image is formed at the infinity, which is possible when the image formed by the object lens, it lies at the focus of the eye lens. So this is the situation here. So in this particular case, this point, this image, it will behave as the object for the eye lens. So because this image which is formed by the object lens, it is at the focus of this object lens and it also lies at the focus of the eye lens. So therefore total distance between the two lenses, or we can say the length of telescopic tube, it is given by the sum of their focal lengths. So from here up to this image, it is the focal length f0 of the object lens, and because this image also acts as the object for the eye lens, which is at the focus of the eye lens. This image is at the focus of the eye lens. So therefore this distance of this object, or we can say this image from the eye lens, is Fe. So total distance between the two lenses, object lens and eye lens, in this particular adjustment of the telescope, it is simply f0 plus Fe, the sum of the focal lengths of the two lenses, the object lens and the eye lens. This is called as the length of the telescopic tube, and it is simply written as L. So for this object, or we can say for this image formed at the focus of the eye lens, the final image is formed at the infinity. Now this is the angle made by the object, right? So this angle will also be same. If this is an angle made by the object as seen directly, it is alpha, then this angle will also be alpha. It is the opposite angle of this, right? So for tan alpha, we will make use of this triangle P0, Fe and I. P0, Fe and I, in this triangle we will find alpha, and in other triangle, this angle is beta. This is the angle made by the image at infinity, so this is beta. So here in this triangle, Pe, Fe and I, we will find tan beta. So when we find the tan alpha and tan beta and substitute values here, we get this formula. On using the values according to sign conventions of Pe, Fe and P0, Fe, because other two terms will cancel out. So we will get the magnification to be minus f0 upon Fe. According to sign conventions, the values are substituted here. So this is the magnification in case of telescope when final image is formed at the infinity, right? Here the length is length of the telescopic tube or length of the telescope in normal adjustment, it is equal to sum of the focal lengths of the lenses. Now comes the second case, when final image is formed at the least distance of distinct vision. So for this, the primary ray diagram is same. There is a distant faint object from which the light rays are collected by this object lens, and this object lens make the image of that very far off object, distant object, at its focal length, or we can say focus, f0, right? The distance of eye lens from this object lens is so adjusted, this can be changed. This is so adjusted that this image which will act as the object for the eye lens, this image will be formed within the focal length of this eye lens, right? So this image will be closer than the focal length of the eye lens FE. It will be closer, right? However, it will be formed at the focus of the object lens always, but the distance of the eye lens is so adjusted now that this image lies at a closer distance than the focal length of the eye lens. So now, whenever the object lies between focus and the optical center of the lens, its virtual image is formed on the same side of the eye lens, or we can say convex lens. So this distance is so adjusted that final image is formed at the least distance of distinct vision, called as capital D, which is 25 centimeter for a normal eye. Now again, if this is the angle alpha made by the object as seen directly, and then this is the opposite angle, this will also be equal to alpha, and this angle will be the angle made by the image, so it will be beta. Now we make use of same two triangles, P naught F naught I for tan alpha, and triangle PE F naught I for tan beta. From these two triangles we substitute the values in which this side is common. This will remain as perpendicular. F naught I, it will remain as perpendicular. It will remain common in both these two values of tan alpha and tan beta, and they will just cancel, and whatever remaining values are left, we substitute them according to sign conventions, and we get the formula for the magnification as this. So magnification in this particular case, it is given by F plus F naught upon minus UE. It is minus UE, it is not FE as earlier case, right? It is UE because now this image is not at the focus of the eye lens but closer than the focus of the eye lens. So that's why we are using here UE, the distance of the this object. This image will act as the object for the eye lens. So therefore we use UE for it. That's the only difference. So this is the formula for the magnification. In this particular situation, when final image is formed at the least distance of distinct vision. Now we can again make use of the lens equation for the eye lens in order to put this formula for the magnification into a slightly different form. For this we apply the lens equation for the eye lens, right? For the eye lens, U is the object distance, which is nothing but the distance of this image formed by the object lens. So it is called as UE, and for V, which is the image distance, it is nothing but D for the eye lens, and FE, it is the focus, or we can say focal length of the eye lens. So on substituting the values according to sign conventions, U object distance as well as image distance V, they are taken as negative, and from here we can find the value of 1 upon UE. We substitute this value of 1 upon UE from here to here, and we slightly, and again also we take this 1 upon, because 1 upon UE is equal to this much, so on the right hand side we take this 1 upon FE common, so inside we are left with only 1 plus FE upon D. So that's why it is taking this form. So therefore magnification in case of the image formed at the least distance of distinct vision is given by this formula. So it is slightly more. So we see that the focal length of the objective, from here if we try to understand how the magnification of a telescope can be increased, we can decide that by looking at this formula. So if the focal length of the object length is more, and the focal length of the eye lens, let me just explain it once more. If the focal length of the objective is more and the focal length of the eye lens is short, in that case the magnification will be higher. And also we compare these two formulas of the magnification in case of telescope. This is the magnification when in final image is formed at infinity, which is only minus f naught upon fe, and this is the magnification whenever the final image is formed at the least distance of distinct vision, which is multiplied by some factor. So therefore it is clear that this value of magnification will be slightly more than the magnification in case of normal adjustment. So this is about the telescope. Actually this is the telescope which make use of the lenses, the glass materials. So the light ray travels through the material of the lens. So such a kind of astronomical telescope are called as the refracting type telescopes, because they make use of the phenomena of refraction of the light. On the other hand, there are the telescopes which make the use of mirrors, right? Concave mirrors or plane mirrors. So such a kind of telescopes are used as reflecting type telescope. However, final image is seen through a through an eye lens, or called as an eyepiece. So such a kind of telescope, it is called as Newtonian type telescope or reflecting type telescope. So this is the tube of the telescope, at the base of which we have a concave lens, not lens but mirror, concave mirror, which gathers or collect the light coming from a distant faint object. So it collect the light and make, because the light rays will come parallel, so it will make these light rays to converge at its focus. But in place of these reflected light rays, now these light rays are not refracted but reflected. They are again reflected by placing a plane mirror in their paths. So we are placing a plane mirror here in order to take these light rays to come out from an opening on the side, right? And this image, final image, is now seen through this eyepiece, or we can say eye lens. So this is how a reflecting or refracting type telescope works. So there are advantages of using reflecting type telescope over refracting type telescopes. On using reflecting type telescopes, there is no chromatic aberration. However, in case of refracting type telescopes, there is chromatic aberration. So second point is that there is no spherical aberration whenever we make use of reflecting type telescope. Both of these properties, or we can say aberrations or errors, arise due to the refraction of the light. Whenever light enters from one medium to another medium, we know that its wavelength changes. Due to that change in the wavelength, the image will not be seen exactly as it appears, right? So the color of that object will change, so it will not be exactly same as it is. So that is called as chromatic aberration. So in case of reflecting type telescope, because there is no refraction, light is just reflected, so therefore there is no chromatic aberration. Also there is no spherical aberration. In case of refracting type telescopes, all the light rays which are coming from the distant star, which are parallel to each other, they are not converged at one common point called as focus. The property of convex lens is that it has to converge all the light rays coming from a distant object at its focus. But in case of a large telescope, where the large aperture object lens is used, where the object lens is of very large aperture, all the light rays do not converge at the same focus common point called as the focus of the object lens. Some are converged closer and other one are converged at a farther point. The light rays which are away from the principal axis, they are called as the marginal light rays, and the light rays which come close to the principal axis, they are called as the paraxial light rays. So these light rays which are marginal light rays away from the principal axis, they converge at a point closer than this focus, and the light rays which come along the close to the principal axis, paraxial light rays called as paraxial light rays, they are converged away from the focus. So not all the light rays are converged at the same common point. So due to this, the image of the object is not clearly made. So that is called as spherical aberration. But because there is no such kind of phenomena of refraction followed in case of reflecting type telescopes, so therefore there is also no spherical aberration. So reflecting type telescopes are also free from spherical and chromatic aberrations. Also, for making use of large telescopes, because large telescopes are required in order to see even a faint object, very faint object. For that, we have to keep the size of the eye lens, or we can say, object lens very large, because object lens has to collect the light. So due to that, the telescope or construction of the telescope becomes very costly. Whereas in case of reflecting type telescope, it is not the case. They are comparatively cheaper, and they can be made of large telescopes because they are also convenient to manage. In case of refracting type telescope, where lenses are used for the large telescopes, they are very difficult to manage. They become quite heavy, wherever the reflecting type telescope are not comparatively that heavy, and they are easy to manage. So this is about the telescopes and reflecting type telescopes and refracting type telescopes, and the advantage of reflecting type telescope over the refracting type telescopes. That's all about the optical instruments. Thank you.